Hello, everybody. Welcome back to Calculus. All right, so now we are at section 2.5 in the OpenStax textbook, volume 1. And this section deals with the mathematical or precise definition of a limit. Okay, now we have talked about limits of different functions at different points. And we even talked about, continuity at the point and continuity over an interval. They all have to do with limits. But what is that limit? It's the value that f of x approaches as x approaches a from the right and from the left. That, I said, was an intuitive definition. It turns out that for mathematical rigor, a more precise definition is required. And that involves, unfortunately, a rather messy kind of a description, all right? And we use two Greek letters. So it may sound all Greek to you, but hopefully you'll have some understanding of the technical definition of limits, which we are now covering in section 2.5. Let's get started. Section 2.5 requires a couple of Greek letters, and so we may just want to learn how to spell in Greek alphabets, in the Greek alphabet. We are not going to go through all of them, but you may recall from your study of trigonometry, we use letters like alpha. That looks like our A, beta, which looks like our B. And just incidentally, alpha and beta give us the word alphabet. And the word alphabet comes from alpha and beta. Okay. The next one is not C, but it's gamma, which looks like this. Right? And then we have delta. And then E is like our epsilon. Their epsilon is like our E, and let's see, epsilon delta, delta epsilon, and then it keeps going on. You have all kinds of things. The last one being omega, which looks like that. The capital letters are all different. A, B, gamma looks like that. Delta looks like this. Epsilon looks like this. Omega looks like this, and there are a whole bunch of other ones. Okay. The next one, by the way, after epsilon is zeta, which looks like this, or z. Anyway, we are going to use two of these, okay? Delta and epsilon in the definition, the precise definition of a limit. All right, so we talked about the intuitive definition of a limit, right? And so that one is the one that says the limit of fx as x approaches a is equal to L. And we are going to now describe what we mean by that one sentence, which has the subject and the verb. If and only if, okay, now we are about to write the characteristic description of what we mean by this statement, the limit of f at a is L. And what we said is, if and only if, as x approaches a from both sides, fx approaches L, okay? Infinitesimally small, get closer and closer to, okay? So we let x get closer and closer to a from both sides without ever reaching a itself. And as you do so, f of x, the associated or mapped values, get closer and closer to L. The reason this is not mathematically satisfactory is because terms like closer and closer or infinitesimally closer have to be quantified in some way. All right, so here is the official, the mathematical or precise. I like the word mathematical because you can have many things precise but not mathematical. This is the mathematical definition of the limit at single point. Ready for this? We are going to say the limit of fx as x approaches a is L, if and only if. So far everything is the same, because what we are about to define, what we are defining is the same thing. We want to define when the limit of f at a is equal to L. And here is the rest of the precise or mathematical definition, okay? Ready for this? Ready or not? For every epsilon greater than 0, there exists a delta greater than 0, this is delta and the lowercase delta, such that, ST means such that, whenever x minus a, the absolute value of x minus a is the distance between x and a, is less than delta, but it has to be greater than 0. Now this part is only to say that x cannot ever be equal to a. You know, that's what we mean by that, as before. Whenever this is true, f of x and L, the distance between these values, can be controlled to be less than epsilon. Okay, it sounds all strange, right? It sounds very weird. I must tell you, I could probably do this in my sleep, okay? When you get trained in mathematics, well, okay, this is one of those things where you could just quote when you're half asleep, all right? And so, you know, I may forget some formulas like the quadratic formula or the double angle formula for trigonometry or something. But if you ask me for the definition, the precise definition of a limit, I could probably do that in my deathbed. All right, so the limit is L if and only if for every epsilon, I need to explain this, right? For every epsilon, somebody gives you a very, very small epsilon, then your job is that you have to be able to come up with delta, positive number, so that as long as x is within the delta distance of a and not exactly equal to a, then the difference between the value of the function and L is less than epsilon, which is that small number, which means, this means that f of x is very close to L. Okay, this means x is close to a and x is not equal to a. All right, so here is the accompanying picture, which you should all be familiar with. All right, so let me go ahead and draw this. Okay, so here's a typical picture of a function f. You want to say, based on this, you know, it appears to be a continuous function. And so the value of the function is its limit at a, right? So you know that the limit of f at a is equal to f of a, which appears to be L, the limit. Okay, so what does it mean in terms of, or in light of, or with respect to this precise mathematical definition? Here's what what it says. Okay, for every epsilon somebody gives you. Okay, so this epsilon can be written or drawn in like this. Now this point is L plus epsilon. This point is L minus epsilon. So you go up and down, you know, epsilon and negative epsilon from L, and then you can think of this upper bound and the lower bound. Okay, so what we're doing is we're trying to establish this target, and it's going to be a really, really small target. Let's say somebody gives you an epsilon that's like 0.01, or maybe somebody else gives you an epsilon that's 0.0001, and they challenge you to a duel. Okay, now I am going to let my epsilon be 0.001. So now your job is, the challenge is, can you come up with a delta so that, okay, and delta would be on the x-axis. This upper or the higher endpoint of this open interval is a plus delta. This point is a minus delta. So as long as this is satisfied, whenever the absolute value of x minus a, which is the difference between a and x, is within delta, and x is not equal to a. So in other words, as long as your x is within this small interval from a minus delta to a plus delta, if your x is somewhere inside of this and not exactly a, then are you guaranteed to hit a point f of x within this interval from L minus epsilon and L plus epsilon? And in this picture, certainly it seems to be able to do that. If you pick this delta, the delta looks small enough so that every x in this interval from a minus delta to a plus delta, except possibly at a, for each x in this interval except at a, f of x seems to be lying within the interval from L minus epsilon and L plus epsilon. In other words, the value of the function fx minus L is going to be less than epsilon. So this delta works for this epsilon. Now the question is, for every epsilon anybody in the universe gives you at any time, can you come up with a delta so that this condition can be satisfied? If you can do that for every epsilon, then the function is, or the limit of the function is L. And if you can't, then the limit of the function cannot be L. That is the precise definition of the limit, okay? So for every epsilon, there exists at least one delta such that whenever x is within the delta distance of A and not equal to A, then the value of the function is within the epsilon distance of L. That is the definition of a precise mathematical definition of the limit. All right, I am going to give you an example just so you know how this applies. Let's say x squared, right? You know the limit of x squared as x approaches 2 is 4, right? How do you know that? Well, because we have studied this and it's continuous, and for continuous functions, the value, the limit is the value of the function. You just plug in 2 here and you get 4. Now graphically, this is what's happening. Let's say this is 2 and this is 4. I'm going to exaggerate this a little bit so that I can illustrate this point well. Okay, so let's say somebody somebody picks epsilon to be 0.1, right? So that's a challenge given to you. Like this person is saying, look, I want my f of x to be within 0.1 of 4, okay? So that means it has to lie between 3.9 and 4.1. Think of this as a bullseye or something. They want you to hit this target, okay? And the question is, can you find the delta so that within the delta, the units of 2, if you pick any x between 2 minus delta and 2 plus delta, I will write this later, okay? Because I will find the delta that would satisfy this. So that if you can find any x delta within the distance d delta of 2, then that number x squared is going to be hitting between 3.9 and 4.1, which is the target, right? So what you can do is this. You can try, let's say 1.97 square is 3.8809. So you actually are not within the target. 1.98, that's a number that's very close here. If you square that, you get 3.9204. That's good. That's within this target. Let's go ahead and color the target to be purple. Okay, the purple target. This number hits the purple target, and it's only 0.2 units away from 0. All right, how about 2.02 squared? That's also 2 units away from 0, 0.02 units away from 0. If you calculate this, you get 4.0804. That's okay too. It's less than 4.1, right? So these two values are both within the target of point or less than 0.1 units away from the number 4, which is the claimed limit. All right. Notice here, these are both 0.02 away from the number 2, right? So we let delta be 0.02. Okay, so this number will be 1.98 and this number will be 2.02. And guess what? As long as my x is between 1.98 and 2.02, in other words, as long as my x is less than 0.02 units, my x value is 0.02 units or less than 0.02 units from the number 2, and it's not exactly 2. It doesn't matter in this case. Then f of x, as you see, varies from, let's see, 3.92 to 4.08. So this minus 4, the difference between these values and 4, would be less than 0.1, right? And so that, of course, is the epsilon. I have picked delta such that whenever this condition is true, you know, that 0 less than the absolute value of x minus 2 less than delta, whenever this is true, then fx minus L, which is 4, is going to be less than 0.1. All right, so that delta does the job for this particular epsilon. Now, this doesn't prove that the limit is 4, right? Because the definition says you have to be able to create this delta for every x. So how do you do that? If you have 3,000 different epsilon values, how do you know that? What delta is? Okay. So the idea, I mean, practically, it's not practically possible to come up with the delta for every epsilon somebody specifically gives you. What you have to prove to prove this statement is that no matter what epsilon somebody gives you, you can find an appropriate delta, oftentimes depending on that epsilon value. And if you can prove that for every epsilon, there exists a delta that would satisfy this expression, then you could then prove that the limit of this function is L, in this case 4, right? I know it's a lot of work, okay, and it's probably too much work for students taking calculus for various reasons. Maybe you don't need to know this much of a theoretical mathematics, and that's why this is not a in the main ingredient of a Calculus 1 course. But this is certainly something that every calculus student should be aware of. In other words, calculus students should know that there is a precise definition, of a using epsilon delta of the limit of a function. All right, so there you could appreciate the mathematical foundations that have established what is today known as the study of calculus. This concludes chapter 2. And now we go into chapter 3, or next we go into chapter 3, which has to do with the rate of change, the derivative. All right, I hope you will have a wonderful day.